One. Hello, welcome back.
Hi.
You're having a good day. It's not raining here. The last video we did, even though we changed clothes. Oh wait, no, you don't know it's a different day. It's not raining here, but I think it was raining where you are now. So
Yep, it's raining now.
okay, so we're going to talk about exponential functions and their graphs in this section. So we'll jump in on that, and let's look at a piece of paper. There's a good old-fashioned story that says if you take a piece of paper and fold it in half until you can't anymore, what happens? So I'm going to do it, and Miss Young was going to go get some toilet paper. You didn't get it. So there's one fold.
You told me not to get toilet paper. You said, I don't really think it's necessary for you to fold toilet paper. And then he proceeded to tell me that he really likes toilet paper. So
6. I think that's 6. And I get to a point where it gets real fat and real small, and I can't fold it no more. Right?
Yeah. And if you're curious about this, you can Google Mythbusters paper folding, and there's a whole thing about it.
Yeah, there's a really cool video. I mean, I don't know if you ever watched Mythbusters, but they did this. This is one of the mini myths that they busted. It's like 3 minutes, but we don't want to. We'll let you guys YouTube that. So what happens as we fold and as we do this? Before I fold it, how many sheets of paper thick is it?
1.
1. Okay. So and once I fold it one time, it becomes 2 layers thick, and so on. After I fold it the second time,
then you got 2 layers on top of 2
layers for a total of 4.
And then you got 4 layers on top of 4.
4 and 4 make 8.
And then 8 on top of 8.
And so on. Okay. So if I go on to the next slide here, I already have those in there. So we can begin to see what happens to the paper as I fold it more and more. I'm going to put you're like on the top middle of the graph. So at 0, 1, I'm going to have a few points here. So let's put in our dots at 0, 1, 1, 2. The next one would be at 2, 4.
This is an interesting graph. You can see that it's actually stretched horizontally.
Yeah, I didn't make my scales correct, proportionally correct, because what happens with the folds is it gets pretty big pretty fast. I don't think I showed you. Like it gets amazing, like my shoes. Okay, my shoe collection has gotten bigger and bigger over the years. Miss Young said nothing goes with this shirt. Look how beautiful this goes with that. I mean,
wait, just so we're clear, we try to match our shirts. I don't know if you've noticed this yet. Mr. Bobby shows up on the video in that shirt, and I'm like, well, I don't own a psychotic Looney Tunes shirt. So this is as close as I could get to matching his shirt, just so we're clear.
And my shoes. So, and by the way,
I didn't bring any shoes.
I just ordered some new ones today too. Yeah. So anyway.
I got some new shoes in last week.
Nice. I'll have to show them in a video. Or you'll have to show them in a video.
Was it you're going to show my new shoes in a video?
Yeah, you probably didn't get good shoes like me, though.
Do you want me to go get them while you're talking through this?
I can talk through this while you do it.
Okay, I'll go get them.
All right. So anyway, these graphs, this is a discrete graph, but what's happening every time, and Miss Young kind of alluded to this, is it's doubling each time, or it's being multiplied by 2. So we're multiplying by 2 over and over and over. If I multiply by 2 over and over and over, it's a power. So it's, make this x. And it would be 2 to the x. It's just multiplying and multiplying and multiplying and multiplying by 2 every time. And when you repeatedly multiply, that's an exponent. So it becomes 2 to the x. So this is our new equation, y equals 2 to the x, or f of x equals 2 to the x.
This is the Dublin function.
Dublin function. Or not the Dublin. Oh, see, I knew they'd be boring. I would be run out of town if I showed up in boring old white shoes. All right. So
they're going to be so cute.
Yeah.
I feel good about them.
Okay. All right.
I haven't worn them yet because I just sit at home all day.
So, that's the definition of an exponential function is a to the x, a number to the variable. We've always had the variable in the base before. But now it's all about the base, about that base.
No treble?
No treble, okay. So that number a to an x is going to be a subtle difference. It's going to make a huge impact on the graph. So let's look at the graph of 2 to the x. Okay.
So let me erase what I just wrote.
I got it for you. So there's 2 to the x, the graph of the exponential function, the basic exponential function for the paper fold. Now, you can't do 0.5 of a fold. So we had a discrete graph of a bunch of points. But if I could double every, double, like, unfortunately, a lot of the z-spread is modeled by, at least in part, by equations like this. They want to actually flatten this curve. You heard that term. It's kind of related to this.
This is the curve-ish that they're.
I mean, it doesn't always go like this forever, thankfully. And if we can, we're not going to talk about that in this video, but I don't want to talk about it anymore anyway, but whatever. All right. So that's what we call the exponential function. Okay. So I want to look at and investigate different values about the base because, like we said, it is, in fact, all about the base. Okay.
All about the base.
I set you up earlier and you didn't take it. So
and I didn't want to do it when I was expected.
Okay. So here are the graphs of the first row. And I know you have the notes, we wanted to graph 2 to the x and compare it to 1.2 to the x and 5.2 to the x. I'll let you look at this for a second and then let Miss Young tell you what she notices or what she thinks about this.
So the first thing I notice is they all have the same y-intercept. I try to find the things that they have in common before I try to find the things that are different. That's just the way I look at things. Another thing I noticed that they all have in common, and we've already talked about asymptotes, it appears that they're all approaching the x-axis. That pink one looks like it might be on the x-axis though, so I might need to investigate that a little bit.
Okay.
And then they're all shaped increasing. So all of them are increasing. All of them look like they're almost trying to touch the x-axis. All of them have the same y-intercept. Those are the things that are common that I see right off the bat.
Okay. Oh, and you can see right there, I labeled the 0.01. Even I did it in pink. Look at me. That was pretty cool.
Beautiful.
So anyway, but why? And Miss Young said this pink one looks like it gets to the x-axis, but it's got those crazy E things on it, which means it's like a whole bunch of zeros and then there's a number. But it's close, but it ain't quite there. Okay. Yeah. So even though it looks like it's just really, really small, but not quite zero. Okay. And that's the idea of an asymptote. Why? All right. Why am I getting wait, I'm in negative numbers for X and I'm getting positive numbers out for my Y. Like if I go to -1, just so I'll make it life easier, why am I getting decimals?
Can we look at the black graph and have this conversation? I feel like it'll be easier to talk about this if we're looking at 2 to the x.
Okay, but I got a negative x. Why don't I get a negative y? That's Young. Oh, that feels good. That makes me feel good. Help me out. All right, tell me what talk to me about why doesn't this go negative?
Okay, so if I think about 2 to the x to a negative exponent, like if x is -1, but we're on the black graph right here, so you can see that's this point right here, -1, 0.5. Now you have to remember back from Algebra 1 and Algebra 2 when you learned exponent rules, okay? So the negative exponent is your reciprocal rule. And so this tells me actually to take the reciprocal of the base. So remember, the negative exponent doesn't make the base negative, it takes the reciprocal of the base. And then it takes whatever power is out there. So like if it were -3, it would take the reciprocal, you'd get 1/2, and then you'd to the third power. So 1/2 times 1/2 times 1/2, which is 1/8. So no negative output here.
No negative, that's why we get the asymptote, because I get more and more fraction-y. Okay, and that happens faster if it's 5.2 in the bottom being raised to powers, because 5.2 gets bigger faster than 2 does. Okay, right. 5.2 to a power gets bigger faster than 2 to a power. Okay,
and smaller faster if you flip it.
And that's why, and so that's the similarities. We have that asymptote and we have the x-intercept. What about the things that are different between these three graphs? I look at this 2 to the x, and that's in the middle. 1.2 to the x is like flatter, and 5.2 is steeper. Why is that?
So even though they're all increasing, it looks like they're increasing at a different rate. The pink one looks like it's increasing faster, and the red one looks like it's increasing slower. And so if you look at the base, because, you know, it's all about the base.
About base.
5.2 is bigger. 5.2 times 5.2 times 5.2 is going to grow a lot faster than 1.2, which is smaller. 1.2 times 1.2 times 1.2 is going to grow slower. It's going to be smaller than 2 or 5.2. And if we threw, sorry, go ahead.
I was going to say, this is an oversimplification of all the stuff you've heard about the spreads of diseases, of the COVID stuff, whatever. We want to try to make that base number a little smaller. Right.
Want the growth to be slower.
Yeah. Now that's, in some cases we would want the growth to be bigger. If this were my bank account, I'd want the pink graph. But if this were spread of a disease or the zombie apocalypse, I would want.
But if this were the medicine that we wanted to be kicking in, we would want it to be really rapid.
Yes, and the cool thing is, all of these models that we just mentioned are modeled by this. Even zombie spread, walking dead. Even the zombies are follow this formula. So, all right, let's turn it around. Let me go back to the slide for a second. We talked about these first three. When the base is bigger than, or those ones, all the bases were bigger than one, we got growth. I want to look at this next row, and what these three all have in common is that they're decimals or fractions between 0 and 1. So let's see what that does, because obviously there's something different here. I don't
know if you pointed this out while I was gone getting some shoes. Oh, we got some feedback. But did you mention that the base can never be negative?
I haven't yet. Oh yeah, I did in the previous slide. The base had to be.
Okay, just making sure.
It was in the slide a minute ago.
Cool.
Okay, yeah, the base can't be negative. We can maybe talk about why later on, but let's finish this conversation, and then we can have that conversation if you still want to. This graph looks like the last one, but not quite the same. I still got that same point that Miss Young was saying, that they cross. They all have the same y-intercept at 0, 1. Okay, that might be something I want to think about or put it up here. And I also have the asymptote deal happening, but the asymptote's like on the other side. But that's weird. Why am I getting it? Why is it like on the other side?
Well, this time all of these lines, they're not lines, all these curves are decreasing. And so now if I think about taking half of a half of a half of a half of a half, like if I'm sitting here eating a Snickers bar 1 half at a time, that's going to get really small really fast as X gets bigger, right? Because that's how many times I'm multiplying 1 half times itself. So this one is, go ahead, what?
I keep taking half of a bite of my Hershey's bar and half of what I have left, and half of what I have left, it'll last forever though.
It will last forever. I wish it would last forever. Now I want a Snickers bar. But anyways, these are decreasing because half of half of half of half of half gets small. Well, thanks for rubbing that in.
I still have one of these. Okay. So a half of a half times half times half is still positive though, and small, but not 0. Right. Okay. So let me go back to the slides. And just for Miss Young's sake, I did say that the base had to be positive.
Okay.
And the base can't be 0 because I could throw 1 or a negative number in there, but they're not going to be an exponential function anymore.
Yeah.
Let's tackle the easier one. Why don't I want 1 in there for A?
Because 1 times 1 times 1 times 1 times 1 times 1 is not very interesting. It's constant.
It would just be a horizontal line, and that's fine, but it ain't getting me anything interesting.
Right.
All right. Now you want to tackle the negative?
Sure. Maybe the easiest way to do this, and it may take me just a second. Are you going to go to the calculator?
Well, I was going to try it in the calculator. You go ahead and do what you're going to do, and I'm going to try to do it in the calculator.
Okay. I don't think I can see, but what would happen is if I had, let's say the base were -2. -2 to the 0 power would be 1. -2 to the first power would be -2. But -2 to the second power would be +4. And so what he's doing here is he's going to see what happens when we graph this. I'm actually not sure. I've never done this.
Actually,
maybe an X in the
yeah,
exponent.
maybe put an X in there.
Yeah. There's that oscillating function.
Yeah, it actually does that. And that's because every power, we talked about this with John Travolta and Touchdown Boy, it would
Right.
alternate signs. But
Right.
not only does it alternate signs at every integer, like every fraction and decimal, and
Right.
it's like, it looks really cool.
It is look really cool. So you get 1, and then you get -2, +4, -8, +16, -32, and it would just keep going like that. Well, this does not follow the pattern of a traditional exponential function. And so we just don't call this an exponential function.
We can do it. It's just not going to be very helpful in everyday life. And
right.
That's why we say, man, we're just not going to do that.
The awesome thing about exponential functions is they model so many natural occurrences. They model like disease spread, they model money, they model when you get at a petri dish and you're looking at cellular growth, they could model cellular growth. Just so many things they model. So this is a kind of a cool function.
Yep, it's probably my favorite chapter. Okay, so kind of the summary of what we just said. Basically, I could have just thrown this slide up and said, hey, here, memorize this, but it probably wouldn't have been as much. It wouldn't have made a whole lot of sense. If that base is greater than 1, then the graph would be increasing. Okay. If it was, but if that base is between 0 and 1, the graph is decreasing. Ms. Young immediately picked up on the y-intercept and the asymptotes we talked about. The domain is all real numbers, and the range is from 0 to infinity, and that parenthesis is critical because you never get to 0, okay? And the function is 1 to 1, and we talked about that last section. The 1, 1, it did pass the horizontal line test, so it means there's an inverse coming. Get ready for it, it's coming, okay?
Maybe they already know.
Yeah, they probably.
Do you guys know what the inverse of an exponential function is? We're not going to tell you yet. To be continued.
To be continued. You have to show up for another lesson. All right, we're gonna do what we've done with every other graph, and we're gonna graph. We have the original parent function 2 to the x, which we talked about a minute ago, and we're going to look at its transformations. What do you think happens? We're going to be a little more efficient with it this time. What do you think is going to happen to this guy?
Well, I see +4, not
4+.
in the exponent.
Wait, I see 4+. I don't see +4.
Whatever, I can read from the function. The function is 2 to the x. So I'll read from the function. The function +4 tells me it's probably going to move up 4.
So if you need to rewrite it, that's fine, but I need to because I'm not, so like that. So we're going up 4. You probably don't need to do that. I'm not going to do that ever again, but if you need to, God bless you, do it. It helps, okay? But yeah, sometimes that's about as tricky as I can be to throw the number in front.
It was exciting. They enjoyed it.
No, they didn't. They're making fun of me. They're laughing at me.
They're probably not laughing at you, but there's probably a pretty hard eye roll that's occurring.
That's what I get. So here's the graph. When I have these all set up, the way I set them up is I tried to make the parent function black in the original. So hopefully I was consistent in that. If not, I'll deal with it. But it moved up 4. I let the calculator do the sketching for me. What would be the y-intercept of the new red graph?
Looks like it would go up from 0. 1, 2, 3, 4.
So this is 0, 4?
That's 0, 5.
Why is that 0, 4? I thought it was 0, 4. Wait, it was.
We started at 1. I was doing the asymptote. I'm sorry.
All right. So I'm talking about this guy right here.
I should listen. I'm like a student. I don't listen. I just answer the question I want to answer.
Yeah, you answer the question. So this point, it was critical before because, and I'm just going to do this once or twice with you. When we were doing this before, up 4, that we did this with the parabola, we did this square root, we did this with the absolute value. All those key points were at 0, 0. The key point now is 0, 1. When I move that point, that's the point I'm going to move. And then this point is now, if I move that up 4, it's going to be at 0, comma 5. I see a lot of students mess this up, and I don't think I'm the only one, right? You see, you agree with that, Ms. Young?
I 100% agree with that.
Yeah, I've seen a lot of students get this, and they can say, oh, yeah, it's going to be up 4, but that's the asymptote. The asymptote, and this is the point, even Ms. Young just messed it up.
Yep.
That asymptote point is at 0, 4. Okay.
Well, and I don't really like, guys, that's not a point. It is like it's a line.
Yeah, that's not even on the graph. This is really, that line is y equals 4 is the asymptote. Yeah. Okay. So I don't want to
understand that line's not part of the graph. That's just to help guide you, because you don't want your curve to cross a value that it can't cross. It can't cross below 4. So you better not, if you were to sketch this and yours crossed below 4, it's not your own.
Yep. And we're going to, be mad and call you names. And
no, I mean, he'll call you names. No, wait, call you names. Where are you?
Where am I?
Are you below me? Are you above me?
I'm above you. Yeah.
He will call you names.
Okay. I won't call you names. I'll just laugh. I'll giggle at you behind closed doors. So, all right. So now let's think about this one again. So this previous one you said was up 4. Okay. What about the one on the bottom here? We said up 4. And again, you should take notes. I'm using the calculator to make better graphs because I'm terrible at drawing. Okay. So what do we expect to happen with 2 to the x minus 5 power?
So this time I notice it's in the exponent. It's happening 2x. So that's the opposite of what I expect to happen. So I'm thinking right 5.
You're thinking, okay, I'm just going to put that in there, even though I'm going to end up turning around and writing it off or erasing it. So because it's in the exponent, that's like being in the parentheses in the quadratic or under the radical. It's happening inside of the operation. I agree completely. All right, let's confirm that Ms. Young is correct. I hope so, or else you're going to have to.
I've been wrong before.
You're going to have to give your master's degree back. Oh, I guess not.
I think, I can be wrong and it's okay.
You can be wrong and keep your master's degree. Yeah, you know what? The nice thing about a degree is they can't ever take it away.
That's right. It's yours.
It doesn't matter how stupid you are. You can still, once you got it, it's yours.
That's not true for a certification, though, just in case you guys wondered.
All right. So that point 0, 1, where is that point on the new graph?
Well, I think it went 1, 2, 3, 4, 5 points to the right.
So it would be 1, 2, it would be right here, I think. And its new coordinates, if I move 5 to the right, that would change the x value. So it will be at 5, 1.
Yeah.
Now you don't always have to do that. I might ask you to label the key point. If I do, sometimes like we tell you things that you might need to know how to do for a quiz or a test. Just
do notice that when we move right and left, a horizontal asymptote doesn't change. It's just going to move right and left, but that doesn't, because it's a whole line that goes on forever, that doesn't change anything.
Yeah. Y equals 0. Dadgummit. Get your pen back. Y equals 0 is still my asymptote.
Mm-hmm.
Okay. All right. So let's try another one. So, oh no. So I got 4 plus on this one. Wait, no, I got 4 minus here. Oh, wait, no, I don't have 4 minus.
You don't have 4 minus. So this time, if you try to read function minus 4, it doesn't work because subtraction is not commutative. Mm-hmm. So this 4 is actually a plus 4. So we might want to rewrite this one.
Yeah, I would probably, this is why rewriting the other one may seem foolish, but this one is a little bit better to do.
Notice I'm leaving that negative sign in front. Also notice that the base is not negative. The base is positive 0.6. The negative is on the outside. So the order of operations here would be first the exponent and then the negative.
So that one's going to be decreased. That part's going to be decreasing, right?
Yeah.
And this part's going to be up 4. And the negative, that in the front, that's like a flipperino over the x-axis.
Yeah, that's Beyonce's move.
Okay, that's the reflect.
Or no, wait, Beyonce's move goes this way. That's the upside down. What's the show with the upside down called?
Stranger Things.
Yeah, that's the Stranger Things move.
Yeah, this. Wow, I haven't used that one yet. So, so all right, there's a lot of stuff going on here. I'm gonna need a little help here. So let me just kind of go over to the side here. I know I'm thinking it's going to do that, right? That's F right there, the unmanipulated one, right?
Yep.
Okay. So if I do all these things, I'm okay with the +4 and the decrease. So if I reflect this guy over, would it be like that?
Yep.
That's not is that okay? Can I do, yeah, I guess, okay. And so I'm going to have that graph doing this thing. Wait, no, this thing. Except I'm going to slide them up 4.
Yeah.
Okay, so let's see if we're right. Just trying to talk through it. Oh, that's super helpful. So moving on to the next slide, we see there's 0.6 the x, and I kind of just walked you through mentally what I was doing in my head. I would have reflected it. So I'd have that yellow graph coming to the x-axis from below, but instead I scooted up 4 units. So this asymptote is at y = 4.
Yeah. And this time it's approaching the asymptote from underneath. Perfectly fine.
Yes.
Perfect. Now, guys, when you put this in your calculator, that dotted line won't be there. We're putting that dotted line there to help you. And by we, I mean,
yeah, I got magic powers.
Or he knows how to use a calculator.
Oh, you know what? I just typed y = 4 in the calculator.
So if you think you know, but you're not quite sure, you can actually just type the asymptote in and see if it looks like your graph is approaching it.
And if you aren't really sure about what this point is, you can hit menu and choose trace and graph trace. And go, I'm on the green graph, so to go to the red or the mustard colored graph, I go press up, and then I just type big old 0. Hey, that point's at 0, 3. Okay. All right. So we good?
We're good.
All right. Moving back. Let's try another one. See if I can't make it even harder. Okay. So we did this one. What about? Oh no. Wait. They don't even look any different.
So this time you've got a negative. This is the Beyonce move.
Okay.
This time you've got a negative. You gotta do that last one?
I couldn't even see that negative. I guess I'm old. No. Okay.
If you like it, then you should have put a ring on it.
Oh gosh. All right. So whatever. So when we had a negative out front, we flipped it vertically. You're saying this flips horizontally?
I'm saying this flips horizontally. What do you not understand about if you like it, then you should have put a ring on it?
Well, what causes that? Why does it flip horizontally? Well, first of all, we talked about moving in. This is the negatives happening to the exponent, right? Like it within the operation. So we talked about horizontal stretching and shrinking with other graphs. When you do a negative, it's a horizontal reflection. So this, what's the first graph doing? What's f of x doing in terms of its graph? I'm going to think about this. That one's
2.5 times 2.5 times 2.5 is getting bigger.
It's growing. So if I flip that horizontally, am I going to get this? But you told me a minute ago, I'm only going to get that when the base is between 0 and 1. The base is not between 0 and 1 now.
So we talked about this earlier. This negative exponent, you have to remember your reciprocal rule. So another way to write 2.5 to the negative x power is the reciprocal of 2.5. We could do this. Maybe we'll look at an easier one or easier way to write this in a second. But this would be 1 over 2.5 to the positive x power. That would be the exact same thing.
Yeah, yeah, and that would actually be a decimal because when I multiply that, I know 1 divided by 2 is going to be between 0 and 1.
I just wrote the wrong thing. Hold on. There we go. Another maybe way to think about this is 2.5 is 5 halves, I hope, right? And so I could write 2.5 as 5 halves. And if you're not sure that 1 over 2.5 is less than 1, then you could write it as 5 halves and then reciprocal 5 halves, and that will become 2/5. And I bet you all are 100% certain that 2/5 is between 0 and 1. And now the exponent becomes positive. So a couple ways to think about that.
Okay, so actually like 3. We could think about it geometrically with a negative. We can do the arithmetic, and it does come between. That base is still what we told you earlier is still valid, okay?
Yeah.
So let's look at and make sure that what we're telling you is not a lie. So here are the next page has the graphs already. If I want to back up. So here's the graph. This brown graph is 2.5 to the x, and if I were to graph 2.5 to the negative x, it does reflect it over the y-axis. Okay, so when you take the negative of the x value of a function, it is a horizontal reflection. So, groovy?
Groovy, man, groovy.
Near as long as we thought it was. We thought that was going to take forever. The whole lesson's going to take forever, but whatever. You're just so you and your Beyonce, so, and Stranger Things. All right, so we were talking about this applying to a lot of things, and we're going to see several examples throughout this chapter, but the first one, and probably the most important one, is about compound interest. When you do a savings account or a credit card, you are charged interest, okay? So, or you either earn or are charged interest. And banks make money because they give you like 1.2% interest or some ridiculously low number percentage interest. But then when you go turn around and buy a house, they charge you like 6 or 7% interest. When you get a credit card, the rates are anywhere from 18 to 20 something percent, 24% as high as I've ever seen. Okay. And that's what your credit score actually does. Your credit score tells the companies, banks and credit card companies, how reliable you are and how likely you are to pay it back. And if you have bad credit history, they charge you higher interest, which makes your curve steeper. Okay. So anyway, this is the formula for either a credit card or a savings account or any kind of interest-bearing account. And it's when you borrow or deposit amount. Principal is that amount. So if I were to take, $1,000 that I get for my birthday from my grandma, maybe $5.
You got $1,000 from your birthday from your grandma?
No, but your grandma, you're the one who had the party in grandma, so my grandma could be rich,
They don't know what you're talking about.
Oh, that was the other class. That was that, yeah.
Just so we're clear, I don't have a party in grandma. I don't.
We're teaching both classes together, and she used an example in AP statistics about her grandma going to a party, and it was just weird. All right, anyway.
It was perfect. It was perfect.
It was perfect, but it had nothing to do with this problem. So anyway, suppose I have $1,000 and I want to save it. And I give it to the bank. I say, here, you take this money, keep it, and you keep it for however many years I want you to keep it. That's the number of years. That makes sense. Interest rate, they're going to say, okay, we'll take your money and we'll give you 2% interest. That's 2% as a decimal. So in the problem, I would put 0.02, okay? And compounded times per year, what that means is they will give me interest only a certain number of times each year. So they may give it to me like every 6 months or 2 times per year. When I have my house payment or on my motorcycle, I make a payment each month. Well, every time I make a payment, they also charge me interest. So you actually get, on most credit cards and on mortgages and vehicles, you're charged interest monthly or 12 times per year.
Right.
And plug on all those numbers in, and then you'll figure out how much you either owe or how much you have saved. So let's look at an example. And 1 is 1.
Yeah, I would just want to bring this up. This 1 is so important. It's what's going to make this growth, okay? The same way if I wanted to look at a markup of 25% on something, like if a store owner and I wanted to mark up a shirt 25%, I would multiply cost times 1.25. That 1 is so important.
Yeah, it really keeps it from being growth. So, All right, so let's look at an example. You want to read this, or you just pause?
I would love to read this.
Okay.
Suppose you get a no payment credit card with 24% annual interest next year as a freshman. So you're all seniors, assuming at this point. Okay. By the way, a no payment credit card means you're not making payments. But
This
the
is
annual,
when they say zero interest for 36 months, like you see that all the time for furniture stores, or like Best Buy is famous for doing this. You can get a credit. You can go into Best Buy, get a credit card, walk out with a TV, and don't have to make a payment for 2 years. But the interest actually starts to build up.
yeah. So it says you deck out your dorm room with a 60-inch TV, an Xbox, and an amazing sound system because you're an idiot, and you spend $4,000 on that. Since you are a poor freshman, you can't pay your bill for 4 years because you don't have a job because you're going to school. Maybe you have a job as like at a coffee shop and you're making like barely anything.
Yeah, and you're
much
buying pizza with it.
Yeah. How much would you owe when you graduate if the interest was computed monthly?
All right, so we have the formula. It's P times 1 plus R over N to the N times T. Okay? And that gives me the amount that I owe. Or the amount, yeah, this will be the amount that I owe in this case.
Right.
Now, we can dig out some numbers here. P was the principal, how much you borrowed. Where is that in the problem?
That's the P in front of the parentheses. It's $4,000. That's how much you put on the credit card. P stands for, he said, a principal, which is initial amount.
All right, that's how much I borrowed. Okay. And 1 is a number, so I'm just going to plug that in there. Okay. Now we need to figure out, the next thing is R. R was the interest rate, right? And I can see that. That tells me right in the very first sentence right here.
Yeah, we just want to make sure we write that interest rate as a number in the number system, which would be 0.24.
Yep. Do not put 24 in there or you're going to owe more than the United States government owes. All right. Now, how many times N? What's N? N, what was N in the?
N is the number of times a year that your interest is accumulated or
charged.
That's the word I'm looking for. Thank you.
So
it says it's computed monthly. So that would be 12 times a year.
We do have to know how many months there are in a year. Okay.
I hope that you know that.
I hope
Please know that.
So that would be 12 down here. But that would also be 12 up here, right?
Yeah. And this exponent is interesting because we're going to do N times T. T is the number of years, which I think is 4 years. We're going to assume you graduate on time. What that exponent is actually finding is the number of times that they're going to make you pay interest. And so the 12 times 4 is telling you that they're going to charge you interest 90. That's right.
Yeah.
48 times in the 4 years.
Okay. So that's going to be a big number. I'm going to just do it here on my calculator rather than trying to erase all that documentation, if that's okay.
I think it's fine. I think that they are perfectly capable of typing this in with you. I can't because I don't have a calculator, but you guys can.
Have it, yeah. So let me get here and do this. How much do you think they owe?
Ooh.
Take a wild guess. I'm gonna take a guess of like you were when you were in high school. That's like an adult.
Not as an adult, but as somebody who's never owned a credit card before.
Yeah, probably as
somebody. I'm gonna say like $4,500.
You think that's fair? That you after 4 years you owe them $4,500?
About $4,500, yeah.
Okay.
I mean, it seems high, but like unreasonable. But like, yeah, because I didn't make any payments. I owe them $10,000.
That's what you owe them.
Guys, this is how credit card debt happens, and it is one of the biggest problems that people have in the United States financially is they get wrapped up in credit card debt and they can't ever get out from underneath it.
And folks, I've been doing this problem for a long time because I actually did this. I got a credit card when they used to actually put books, like when you buy actual physical books, they would put credit card applications in them. When I was in college, I don't know if they still do that or not, but I bought a book and there was a credit card application in it. I took it out, filled it out, got my own. I was doing great. This is cool. I got a credit card until I bought $500 diamond earrings for my girlfriend. I couldn't pay for her, and I didn't. So anyway, don't do this. All right,
Don't do this.
don't do this. At least I wasn't $4,000. I mean, I got it paid off, but it just didn't happen as quickly as I'd like. So
Yeah.
All right. So, all right, now let's talk about my favorite number in the whole world. Everybody loves pie. I mean, I like pie. Don't get me wrong. A good slice of blackberry pie, that makes me happy. Apple pie.
Coconut cream pie.
Yeah. And so I'm all about it. But there's another number like pi that's actually more relevant for us in this situation and a lot of higher mathematics, and it's a number E. Yeah, I said that right. It's E, like as in the letter, not like, So it's named after some, he was Swiss, wasn't he? Leonard Euler. I think he was Swiss.
I don't actually remember his origin.
But anyway, some old dead math dude, like did a lot of work with this. And you're like, if you're really important, they name something after you, like with a lowercase letter. So anyway, that's what he is. And what we're going to do.
He said his name is Euler, but it's actually spelled like this.
Yeah, I think he was from Switzerland or something, but because
Euler.
Yeah. Okay. So what we're going to do is put bigger numbers in for n. Like I'm going to start with 10. I'm going to put 10 here and 10 here and see what happens. Okay. If I put 10 here, that would be 1/10 to the 10th power. But then like if I put 1,000,000 in here,
that's well, it wouldn't be 1/10. It would be 1.10. Yeah.
Yeah. 1.1 to the 10th power. And that's like, can't be that big. Okay. But then like if I put like 100 in here, this part inside the parentheses is going to get smaller, right? And but raising it to a power is going to kind of make it bigger because no matter what I put in here, it's going to be bigger than 1, right?
Yeah.
That means it's growth, and this is going to get bigger. So it's going to like this part's going to get smaller, and this part's going to get bigger, and there's like a push pull. So I don't know what's going to happen.
Right.
Okay. So
let's check that out.
Let's check it out. So if I go here, and clear out your Euler. If I go to the next page, I've got it already, and I did it with tenths. So 1 plus 1/10 to the 10th power is 2.59. Oh, okay, all right, I can deal with that. So let me add another 0 there. So I want to do 1/100 to the 100. Okay, it's getting bigger. I like it. It's good. So let's.
We could go to Desmos and do this with a slider, and you could just slide it, and you could see that number.
I could do
changing.
Yeah, I could. I could have done that here too. Right, 2.1. Didn't get too much bigger. You want to try 1,000,000?
Sure. At what point does it break the calculator?
I don't know. That's a good question. Probably like now, maybe. Okay. All right, now wait a second. That's like, there's more to it. Okay. So I'm going to be careful here. I'm going to add, oh, wait a second. That wasn't good. Go back up here and add another 0. Add 3 more zeros. Those look to be the same, but this guy was that, and then this other guy with the more zeros was that. So they like agree to the first 5 decimals, and then they start differing. Okay, they're beyond the calculator. And eventually I could keep adding more and more zeros, but it's converging or merging or whatever you want to call it. It's getting closer and closer to some number, and that number is on your calculator.
You might say it's approaching.
It's approaching. And it actually is in our calculator. It's so important. It's got its own space. Pi, E, imaginary. I think we were in here for the imaginary numbers earlier.
Mm-hmm.
If you choose this, it's actually programmed in your calculator. And if I actually grab the decimal, I guess it shows me more of the decimal. This is another number like pi, like square root of 2 that never repeats, never terminates. It does have a 1, 2, 8, and then like a 1, 2, 8 again, but that never happens again. That's kind of weird. That there is kind of like a little pattern there, but that doesn't happen. That doesn't ever happen.
Yeah.
So anyway, this number is like critically important for a lot of exponential function graphing, and it ends up being super important if you go on and take calculus.
Yeah, this is called the natural base, actually.
Yes.
Because it occurs so often naturally in different growth patterns.
And the graph of it, not surprisingly, is growth. Why? I mean, why does this make sense that it's growth? Is because E's 2.718, blah, 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 and 2.718 is bigger than 1.
Yeah.
Okay? So it's exponential growth. It's very common. It's used a lot. And it's, it'll be your new friend. Okay? So say hi, new friend. You're supposed to say hi.
It says, eek! I'm excited.
Oh my gosh, you're such a nerd.
No?
All right, so let's look at some of these graphs. Or let's actually think through these, and then we'll look through all 3 of these graphs, okay? So what do you think is going to happen to f of x compared to the basic graph of e to the x?
-2 on the inside of the function or on the inside of the exponent happening directly to x? Probably right 2.
I concur. What about the next one?
2 things are happening on the next one. We have a upside down, wait, what's that show called again? Stranger Things flip. And we have a vertical stretch.
Okay. What about the last one?
Looks like a +3 on the outside. And so that +3 on the outside is going to make it go up 3. We also have a Beyonce flip here. So it's going to reflect over the y-axis there. So we're going to reflect and become decreasing. And then we're going to shift up 3.
Okay. So we're going to be, Miss Young has made her predictions, and we'll find out if she is correct. So
Bum, bum, bum.
bum, bum, bum. So I'm just going to quickly roll through these. And so the first one she said was right 2. And again, I kept the basic graph black. So there's the basic graph of e to the x. And sure enough, that scooted over 2. Okay. What about the next one? She said it was reflected vertically, a Stranger Thing, and stretched. So that was a little harder to see, but if you look at this point, that's the 0, 1 that we're expecting, right? Look at its partner on this brown graph. Where is it now? It is at 0, -2. So I say you're right. And then the last one, it's this red graph, she said, would be decreasing because of the negative in front of the x. And again, we have the vertical shift up. That asymptote would be y = 3. So I think we've done a good job. Good job, you. Pat yourself on the back. All right. And that's all she.
I bet you guys are so thankful that's over.
Wow, that wasn't even nice at all. You have.
That was a long math video.
But they got to see my amazing shirt, so
they did.
All right.
And I'm sure that they are just like excited.
Yeah, they're already gone. Bye.
Oh, they left.